Hello guys, believe it or not, today is the last lesson that will be accompanied by a graded activity. And this lesson is moving sources of waves. And you guys did the activity already, so I'd like to give you the notes so you can make sure you know how these things were supposed to turn out. And then I'm going to ask you some questions based on these notes. So the first thing I'd like you to notice is we're talking about an object like an airplane that's giving off sound waves. And at the same time, the object is moving. We want to know, what does it do to the sound waves? How will they sound? How will they change? What's going to happen as we adjust the speed of the plane? So let's start out with a plane that's not moving at all, that's just sitting still on the runway producing noise. Under this circumstance, all of these waves will trace back to the point where the airplane is. These waves are known as concentric circles. In reality, they are three-dimensional, so they're concentric spheres. But the key word is they're concentric, meaning they have the same center point. Meaning that the wavelength is the same in all directions. The frequency that you would hear would be the same for all observers. Obviously, further away would be less loud, but it would still be the same pitch. It would still be the same note. Okay, so that is for objects that are at rest. For objects that are moving, you're no longer going to have symmetry. You're no longer going to have concentric circles. You're going to have your object moving, and each circle is centered around where it was created. So that first circle was created when the plane was here. The circle it's making right now is centered around this spot, and then this spot, and then this spot. All the waves have a different center point. The center point shifts with the direction that the plane is moving. You're going to have something that looks like this. Instead of a plane, I made it a tuning fork. You can imagine the tuning fork is moving to the right at a certain speed. And each wave is created when the tuning fork is in a different position. I color-coded them. So the red tuning fork corresponds to the red wave. That's the wave that was created first. It was created when the tuning fork was in that position. The tuning fork moved to here, made the second wave, the third wave, the fourth, the fifth, and finally the sixth. Each wave is shifted in the direction the tuning fork is moving. What that's going to do is make the waves compress in the direction of motion and spread apart in the direction where it's moving away from. This guy will measure a small wavelength and a high frequency. This guy will see the waves far apart, and he'll see a low frequency. So these two will not agree on what note this object is producing. We can see this effect. It's called the Doppler Effect. Anytime we have a moving source of sound coming towards us. So in this case, it's going to be a rescue vehicle. And hopefully you heard the change in pitch as that thing went by us. High frequency when it's coming towards us, and then it goes flat. That is a lower frequency when it goes by us. It's called the Doppler Effect. We can see the same thing with something like a motorcycle. You hear that? That is the change in pitch as it is zooming by us. High frequency when it's coming towards us, low frequency after it passes. Finally, here it is with some race cars. And you'll notice really well how they kept the frequency constant when they had the camera inside the car. The person inside the car doesn't hear the Doppler effect. But the people outside, when the car went zooming by, you heard that again sound as the frequency changed. Doppler effect doesn't just happen with sound waves, it happens with all waves, including light. So as crazy as it seems, that if you took a star and had that star moving away from the Earth, the color of the star would appear to change because the frequency would appear to change. Same thing if the star was moving toward us, toward the Earth, it would shift toward the blue end. So these are called blue shifts when an object's moving towards us at a really high speed, and a red shift when it's moving away from us at really high speeds. Realize that you're not going to see the Doppler effect unless something is traveling really close to the speed of light. Not with your own eyes anyway. We have sensitive equipment that can detect it at smaller speeds. Same thing with sound. You're not going to notice the Doppler effect unless the object is traveling close to the speed of sound. So it's got to be going pretty darn fast. At least 50 miles an hour, which again isn't super close to the speed of sound, but you're not going to hear it when someone just walks by you. Okay, they have to be traveling at a relatively high speed. Next, I'd like you guys to look at an object that is traveling at the speed of sound. This one's not quite at yet, but you can see it's traveling really fast and the waves got really close together. Now it's traveling at the speed of sound. Now the waves cannot get away from the object. All the sound waves pile up in front of the plane. This buildup of sound waves creates a region of turbulence, high pressures all building up together, and this is known as the sound barrier. At one point, we weren't sure whether or not anything could ever travel faster than the speed of sound, and it turns out that it could. It turns out that this is the vehicle needed to break through the sound barrier, and this, Chuck Yeager, is the guy who broke through the sound barrier. He did so on October 14th, 1947. The amazing thing is Chuck Yeager is still alive and kicking. Finally, we have an object that has broken through the sound barrier and is now traveling faster than the speed of sound. Oftentimes when we're moving this fast, instead of giving an actual speed in miles per hour or meters per second, we might say something like Mach 1.5 or Mach 3. What that means is Mach refers to the speed of sound. So Mach 1 would be the speed of sound. Mach 3 would be 3 times faster than the speed of sound. Mach 1.5, that would be 1.5 times the speed of sound. Again, the speed of sound changes based on temperature, but at room temperature it's somewhere around 343 meters per second. So if you're going Mach 3, you're going over 1,000 meters per second. Okay, and guys, that's actually, one last thing. This buildup of sound that you see not in front of the plane, but you see it behind the plane, that is what is known as a pressure barrier. And when this pressure barrier passes by you, you will hear what's known as a sonic boom. A sonic boom is a continual phenomena for something traveling faster than the speed of sound. You'll only hear it once, even though it's constantly being created, because you only hear it when that high pressure region hits your ears. Different people will hear it at different times. All right, so again, that's called the sonic boom. And you can see it's kind of like the wake behind the boat. When the boat's going faster than the water waves, the waves build up behind the boat, and that creates an effect similar to the sonic boom when that wake hits you. Oftentimes these pressure buildups can cause humidity in the air to condense, and you can actually see that cone of high pressure surrounding the plane. Here you can see it forming and disappearing based on the conditions in the atmosphere. Okay, and again, when that cone hits you, it produces your sonic boom. And you'll notice that the people heard it after the plane went by. Again, that weight, that pressure buildup trails behind the object. It's a buildup of pressure. When it hits you, it creates a really loud sound. Anyway, guys, I know I went through that pretty quickly. Normally, we'd be able to have questions as we did it, but hopefully I made it clear enough that if you pause when I was a little more confusing and replay it, you'll be okay. Anyway, there are some questions online for you, and when you're done with those, just hit submit, and that will be the last of your graded assignments.